In a previous video, we saw how Hamiltonian mechanics for 1 degree of freedom was equivalent to 12 different characterizations that physically really meant determined and reversibility. Today we're going to look at the multiple degrees of freedom case. We're still going to have determinists, but we'll see that we'll need another condition to get everything, which is the idea that the system decouples in independent degree of freedom. And we'll see what that means, and we'll also see how mathematically it maps to the idea of symplectic geometry, which is the mathematician way of studying Hamiltonian mechanics. So let's get started. First, let's review Hamilton's equation for multiple degrees of freedom. We're going to use this very compact notation. This is the derivative of position with respect to time is equal to the partial derivative of the Hamiltonian with respect to momentum, and the derivative of momentum with respect to time is equal to minus the partial derivative of Hamiltonian with respect to position. Right? These are exactly the same as the single degree of freedom, except that instead of having two equations, we have two equations for each degree of freedom. Now, we want to write this in a more general form because we want to understand phase space as essentially a single set of variables. And so we introduce this symbol xi for grouping both position and momentum. And then we have the derivative of all the variables with respect to time, which means both position and momentum. And this forms a vector field, right? This vector field S upper A tells us where the states are moving in phase space. And what we're basically saying is that there is a relationship between this SA and the partial derivative of the Hamiltonian. And you can kind of see here that this kind of looks like a gradient, but this is not in terms of Q and this is not in terms of P. So you basically are switching the variables and introducing a minus sign. And if you've seen the previous video of single degree of freedom, we saw that this was a 90-degree rotation in phase space. And this is exactly what we're going to do again here. We introduce a matrix omega that does a 90-degree rotation within each degree of freedom. And we can also think of this matrix as being a block matrix where the QQ part is equal to 0, the PP part is equal to 0, and the mixed QP and PQ parts are equal to the identity or minus identity. So only when you have a matching I and J, you actually have something that is different than 0. And so now we can write that the displacement field, this displacement vector field that tells us where things are going, is the gradient of the Hamiltonian rotated 90 degrees with this rotation. And you can verify that this is true if you take this matrix and you multiply. You're going to get that 0 times this is 0, 1 times this is this, and this basically goes up. And this effectively takes these elements and brings it down with a minus, and these are the Hamilton's equation. So this is a compact way to write the equations. We can, instead of applying this to the omega to the gradient, actually makes is going to make it easier if we apply it on the displacement field. So we have that S lower A is the displacement field rotated 90 degrees. And if you go, you can verify that this is the same. You're going to get the same equations because these are only the terms that are non-zero, and therefore the Qi is going to be mapped to a Pi, and the Pi is going to map to a Qi. But this element, since it's this element here, this is going to get a minus sign, and so you get this minus sign. Okay, so this is another way to look at the Hamilton's equation, and this expression, it's sort of a generalization that makes it so that it's exactly the same in the single degree of freedom, in multiple degrees of freedom. It's a way to write the equation always in the same way, in one essentially vector form, so that everything is nice in a general way, that we can prove theorems that are valid for all of different conditions. Okay? So one thing that we should be clear is that, yes, this omega AB performs a 90-degree rotation, and it does it by essentially switching the position between a position component and momentum component and adding a minus sign. So if we look at this four-dimensional two-dimensional representation of four-dimensional space, the component along Q1 goes into the component along P1, and the component along P1 goes into minus Q1, and sort of something similar happened for the other degree of freedom. And of course, there are multiple ways to perform a 90 degrees of rotation in this four-dimensional space. Actually, there are infinitely many. And it's only the rotation defined by omega AB that works. So it's that rotation is special, and we'll see that also this omega AB have other geometrical meaning that are going to be a little bit more interesting physically. Okay, so we have this. And now we want, in the spirit of reverse physics, we want to find the conditions that allow us to understand a little bit better what happens, and give a better characterization of Wheel's equation. One thing that we saw in the single degree of freedom was that the divergence of the flow of this displacement field is zero, and so we're gonna make the same calculation here. So we take the divergence of S upper A, the displacement field, and this means taking the derivative first with respect to the Q parts and then with respect to the P parts. And using the Hamilton's equation, we can substitute to this with the derivative of the Hamiltonian, and the same here, we can substitute using the Hamilton's equation, and then we just have the partial derivatives, the mixed partial derivatives, and of course these derivative operators are going to commute, and there is a minus sign, so of course this is going to zero. So using Hamilton's equation, what happens is that the displacement field is divergenceless, right? If the Hamilton's equations are valid, then we have a divergence field. Another thing that we saw in the 1 degree of freedom was that there was a link between the divergenceless of the field and the fact that the Jacobian was unitary. So we do the same calculation here. This represents the momentum and the position after a single time step, which is basically the same value as before, plus the variation given by the displacement field. This then is the Jacobian matrix that represents the change for vectors, and we can take the determinant of the Jacobian matrix, and what happens is that since it's a block matrix, is going to be the determinant of this times the determinant of this minus the determinant of the two other terms. And what happens is that these are dt squared, so they are going to be a negligible contribution, and so the contribution that matters are the I multiplied with the I, this delta connector multiplied with delta connector, so that's going to be, the determinant is going to be 1. Then we're going to have the determinant of this multiplied by the determinant of this, which is 1, which is just the determinant of this, which is basically the divergence along the Q, and this other part, the determinant of this, is going to give us the divergence along the P. So this term here, the first order term, is exactly the divergence of the field. So the change in the Jacobian determinant is going to be given to a first approximation by the divergence of the field. But since the divergence of the field is 0, then that means that the Jacobian determinant does not change, and vice versa. These two conditions are exactly the same. Right? So the fact that the Jacobian determinant of the time evolution is unitary is an equivalent condition to saying that the divergence of the displacement field is 0. Now, if you recall the geometric meaning of the Jacobian determinant, it's a multiplicative factor between past and future volumes. So if the Jacobian determinant is greater than 1, volumes are going to grow, and if it's less than 1, they're going to shrink. And so saying that we have a unitary Jacobian is exactly saying that volumes are conserved through the evolution, or that densities are conserved through the evolution, because densities are quantities divided by the volume. So if the volume doesn't change, the density does not change. So all these four conditions are equivalent to each other, because if we impose one, we impose essentially all the others. Now the question is, are these conditions equivalent to Hamilton's equation. We saw that Hamilton's equation implies these conditions, but is it true the reverse? Can we get Hamilton's equation from implying this condition? So let's just make a calculation of how many components are there and how many of these calculations set. So the conditions that we have the divergence field or the Jacobian unitary essentially specify a single constraint in the displacement field. We have one condition on the displacement field, and these are 2n minus 1 component. And then if we make a choice of the Hamiltonian, this provides another constraint. So this constraint plus the Hamiltonian gives us, leaves 2n minus 2 n components free. There are still these choices that need to be made. So what we see is that if we have a single degree of freedom, then 2n minus 2 is equal to 0. So these conditions are enough to recover Hamilton's equation for 1 degree of freedom, but if we have more than 1 degree of freedom, this 2n minus 1 is not 0, and so there are choices that are still free, and so we haven't constrained fully the displacement field, and therefore we haven't fully characterized the evolution. So while it's true that Hamiltonian evolution implies all these conditions, it is not true that these conditions imply Hamiltonian evolution. So now we have to figure out what else is there, what are the things that are actually equivalent to the evolution of Hamiltonian mechanics. When we looked at the single degree of freedom, we had this interesting fact that the divergence of the displacement field being 0 was equivalent to saying that the curl of the rotated displacement field was 0. And this is only going to be valid for a single degree of freedom. But let's go and see what happens to the curl of the rotated displacement field. If you remember, we note the rotated displacement field with a lower index, and this is equal to the upper index multiplied by this rotation matrix omega. And so if we use Hamilton's equation, this term, the rotated displacement field, is just the gradient of h. So this is the gradient of h, this is the gradient of h. And now what happens here is that we essentially have the mixed derivative of h in the two different permutations, which are exactly the same, with a minus in between, and so this is just 0. So if we use Hamilton's equation, we can show that the displacement field the rotated displacement field has no curl. And this does work in reverse. If we assume that SA is curl free, right? So if we assume that this is 0, then we know that this can be seen as the gradient of a potential that we call h. And since we know that this is the rotated displacement field, we can write it in this form, and therefore this is these are Hamilton's equation. So this condition, the condition that the curl of the rotated displacement field is 0, is actually an equivalent condition to Hamilton's equation. Okay, so this matrix, this rotation seems to be important because, again, we start getting a condition that is equivalent to Hamilton's equation. And so one of the things that we had seen for a single degree of freedom was that this omega, if we give it two vectors instead of one, and we use it as a sort of product, we saw that this had the geometrical meaning of actually calculating the area. And so if the area were conserved, then it meant that this omega during the evolution remains the same metric. So when we evolve the system and we transpose this metric during evolution, it's exactly the same way. Now, of course, this is not going to work in multiple degrees of freedom because the assumption that the volume is conserved is equal to Hamiltonian mechanics does not work, but let's still see what happens. So this is going to be the matrix omega as it is being moved by the evolution, and it basically means taking the standard omega and multiplying on each side by the Jacobian. And under an infinitesimal transformation, we saw what the expression of the Jacobian was. It's basically the identity plus the change given by the displacement field. And so we have this in one side and the other side, and you can pause if you want to make sure that all the indices are doing the right thing and so on. But what's important here is that the first term in this expression is the product of the two identities. So what happens is just that this matrix is just changing the indices, and it becomes the original matrix. And then we have the first term, which is this multiplied by this multiplied by this, and again the effect of this in terms of the omega is just to switch d with a b. And we have the other term, this times this and times this, and again the effect of this delta connector here is just to change the C index in a index. And then we have second order term which we are going to ignore. Now what we're going to do here is that omega is just a matrix made of constant, so we can just take it and bring it inside the partial derivative, and we can do it on one side and on the other side as well. Now omega here, you can see that this is contracted with the first index, and this is constructed with the second index, and these are different terms because omega is antisymmetric. So if we switch the order, you get a minus sign. So we switch the order such that we are always contracting with the first index, and then a minus sign appears. And you see now the first term here, it's the partial derivative of A with SC omega CB. So again, this displacement field multiplied by omega, but this is just the rotated displacement field. And the same thing here. This is just the rotated displacement field. And so this is the condition that the curl is zero. And so this matrix omega, which is called the symplectic form in math, it's conserved exactly when the rotated displacement field has a curl of zero. So this is another fully equivalent condition for the Hamilton's equation. Now, if you studied the Hamiltonian mechanics, you might know what a Poisson bracket is. And if you know what it is, you might also know that this Poisson bracket can be expressed as a function of omega, actually the inverse of omega. And this is the same, works the same in a single degree of freedom and in multiple degrees of freedom. And the point being is that if omega is conserved, then the inverse of omega is also conserved, therefore the Poisson brackets are conserved. So conserving the Poisson bracket is the same as conserving omega, conserving the symplectic form, and therefore this is another condition that it's fully equivalent to Hamiltonian mechanics. So okay, so we have two sets of conditions that we found. One, there are the equation and conditions that are exactly equivalent to Hamiltonian mechanics. The fact that the curl of the rotated displacement field is zero, that the symplectic form is conserved, and the Poisson bracket is conserved. And then we have these weaker conditions, that the Jacobian is 1, that the divergence of the displacement field is 0, that the densities are conserved and the volumes are conserved. So these are weakened conditions. And we want to understand exactly why is it that the two sets of conditions are the same for a single degree of freedom, but they're not the same for multiple degrees of freedom. In the single degree of freedom, we saw that if we take two vectors, v and w, and we apply to omega, what we get is the area of the parallelogram that these two vectors make. And so you would have that the conservation of omega means conservation of area, and therefore everything works. This is because a two-dimensional area in a degree of freedom correspond exactly to the volume. So conserving volumes in conserving areas, which means conserving the symplectic form. Now in multiple degrees of freedom instead, omega does something more, because again it operates on two vectors. So if we are in a single degree of freedom, again we are getting areas. But if we are across degrees of freedom, we don't get actually areas, we get 0, because these cross terms, when Q and P's are on different degrees of freedom, this term would be 0, and so we just get 0. So the symplectic form is doing something different. It's still giving us areas on each degree of freedom, but it's not giving us area across degree of freedom. So it's not really just getting us a geometric area, geometric volume as you might expect. So what happens? And one way to look at it, one way to understand it is, again, think of of omega as a block matrix, which is essentially the outer product between the cross product within a degree of freedom. This calculates the actual volume within a degree of freedom. And then the identity, you can understand it as a scalar product across degree of freedom. So in a sense, omega is keeping track of orthogonalities, of what is the angle, let's say, between degrees of freedom. And if two degrees of freedom are orthogonal, you're taking two vectors from these orthogonal degrees of freedom, then you get a zero. Another way, sort of an analogy to understand this, is to understand omega as really essentially some type of variation on Pythagoras theorem. So if you express omega in terms of the differential, you're going to have that you are summing the product of the differentials between Q and P's for each degree of freedom. And you can sort of understand this as taking two sides of the triangle, which would be dq1, dp1, and dq2 and dp2, and these would be essentially the areas of these sides. And since these two are perpendicular, the area on the hypotenuse would be the sum of the two. And I do think this can be more of an analogy. I think probably that if you do the correct projection in the n-dimensional space, you would actually get this expression, but I wasn't able to actually do it. I didn't actually do the due diligence to do it. So I think for now it is an analogy, but if somebody is able to actually make this more than an analogy, please let me know. So this is kind of how we can think about it. And in a little bit more precisely, what we can do is compare the two types of geometries that we have in differential geometries. One of them is the Riemannian, the pseudo-Riemannian geometry that is also used in general relativity, and the symplectic geometry, which is this one with omega, that is used in phase space. In this case, in the Riemannian case, we have what is called a metric tensor. And the metric tensor is essentially an inner product. It takes two vectors and it gives you the inner product. And this defines the lengths and the angles. So if you have if you take a differential, what happens is that this is going to tell you the norm of the differential, and it's just going to be one side of the differential contracted with the other side. And if you are in Cartesian coordinate, this is just all the dx's for all the different components squared and summed. And what's important is that this is a symmetric tensor. Like if you switch I and j, you get the same thing because the inner product is symmetric. And again, this defines the length and the angles. It defines the norm of vectors and defines the angles between vectors. In symplectic geometry, you have a symplectic form that kind of works like a metric tensor in the sense that you give it two vectors and it gives you a number, but it's not an inner product. It's not a scalar product at all. And the privileged coordinate in symplectic geometry are not the Cartesian coordinates, are called canonical coordinates. And in these coordinates, the symplectic form has its simplest expression, which is the product of the differentials in the respective Q and P's, and then sum them. And so the symplectic form defines a geometry, but it's not the same geometry that we are used to, like in terms of distances and angles, because it does not define distances, it does not define angles within a degree of freedom. There is no sense that there is a 45 degrees between momentum and position, because they are different units, so the angle is not really well defined. But you define areas in degrees of freedom, and that's why the symplectic form is antisymmetric. If you switch the order, you get a minus sign, and that's really because we're calculating areas, and areas can be positive or negative if you flip them. And then what you define are essentially angles between degree of freedom. You know when you have orthogonal degree of freedom, and that's what the math keep tracks. And so it's a different type of geometry, but it's the correct geometry for phase space. So to give you an understanding of how this works, suppose that this line here represents the plane of position and momentum for 1 degree of freedom, and this is the plane for the 2nd degree of freedom, right? So directions, like lengths in this distances in each plane they're not defined. What we define are basically areas. So this segment here represents an area in position and momentum for the 1st degree of freedom, and the 2nd degree of freedom, this is the area for the 2nd degree of freedom. And of course you can create volumes, right? And volumes are just going to be the product of the respective area, because these are orthogonal to each other, and we said the metric, the symplectic form knows that two things are orthogonal. So when we are conserving the omega, what we are doing, we are essentially mapping this area to a new degree of freedom, right? But still the area remains the same. In the same way, we're mapping this area to basically an area of the same size in a different degree of freedom, and we are preserving the orthogonality. If we started with orthogonal degree of freedom, the mapped degree of freedom will be orthogonal as well. And then, of course, if you preserve the areas and you preserve the orthogonality, you are also going to preserve the volume. But the inverse is not true. You can preserve the volume without preserving either the orthogonality or the sides of that parallelepiped. So let me give you an example in which that happens, in which we are shrinking the area on 1 degree of freedom while stretching the area on the other in a way that the volume remains conserved. So in this side, right, we have that the velocity is momentum over m, and the change in momentum is proportional to the negative momentum, which means the particle is slowing down, and these are the equation for a particle under linear drag. On the other degree of freedom, instead, we're going to do the opposite. We are going to increase the momentum proportionally to its momentum. So we are basically making things faster and faster while in 1 degree of freedom, while making them smaller, slower and slower in the other degree of freedom. So now we can check whether the volume is conserved, and to do that we can just calculate the divergence of the displacement field. And so the divergence of displacement field is the derivative of SQ1 with respect to Q1, of SP1 with respect to with P1, and so on. So SQ1 is P1 over M, and we put it here. SP1 is minus BP1, and so we put all the other SQ2 here and SP2 here. And now we calculate the derivatives. And the derivative of P1 with respect to Q1 is 0. The derivative of P2 with Q2 is 0. The only thing that are non-zero are these two derivatives, and this is the derivative with P1, so this is going to be just the constant minus B, and this derivative is just going to give us the constant B, so minus B plus B is 0. The divergence of the displacement is 0. The volume is conserved. Now we can instead verify that we don't have Hamiltonian mechanics, that the volume, the areas in each degree of freedom are not conserved. And to do that, we simply look at the curl of the rotated displacement field, and we are going to see if we calculate this component of the curl, this component is not going to be 0. So we are going to calculate the component on with respect to Q1, P1. So we have Q1, P1 here minus P1, Q1. It's the usually a switcheroo of the curl. And so now remember, this is the rotated one. So we have to get the corresponding component of the displacement field itself, which is going to be the Q1 times the omega Q1, P1. And we do the same thing on the other side. The Q1 becomes the P1 with the the part of the symplectic form. Now we do the substitution. SQ1 is this, SP1 is this, we put them here, and again we are deriving Q1 with respect to Q1, so this is 0, and here we're deriving minus BP1 with respect to P1, so this would be minus B times minus 1 times 1, so this minus B. So the curl is not 0, and so this system of equation does not emit a Hamiltonian. It's not a Hamiltonian system. The volume is conserved, but we are not conserving the areas on each degree of freedom. Okay, so we have a good understanding of what's happening to the geometry. What happens is that we have this geometry where we have areas in each degree of freedom that are going to be mapped to equivalent areas, and that degrees of freedom, as they are mapped to things that remain orthogonal. If you have something that is orthogonal, when you're mapping it, it's going to still be on orthogonal degrees of freedom. And now we have to understand what is this in terms of the physics. What does orthogonality in terms of this degree of freedom turn into physics, right? So, because we have our system of equation that is a Hamiltonian mechanics, and we saw that this is conservation of volume plus conservation of orthogonality. We saw before in the previous video that conservation of volume means deterministic and reversible evolution, because you are taking the volume counts the number of states, so we're taking region to regions by conserving the number of states, and therefore this is deterministic and reversible evolution. But what does it mean that the degrees of freedom are orthogonal? So, well, let's think about it. If the degrees of freedom are orthogonal, the total number of states is just the product of the configuration of each degree of freedom. And so all the combinations across the degree of freedom are allowed. We can take any value here, and we can take any value here, and we have the state of the whole system. And this means that the choice configuration of one degree of freedom does not constrain the other. So if I pick these values, well, we're still free to pick whatever value we want here. And therefore, the idea is that the degrees of freedom are independent. So orthogonality in phase space means that the degrees of freedom are independent. And what does it actually mean to be independent? Let's see that with an example, because it's better to have an idea of an example of where things become non-independent. So suppose that we have a rabbit farm, and we can imagine the state of the farm being described by the number of male and female rabbits. And so if I say there are 231 female rabbits, well, this poses no constraint on the male population. I select here 231, we can still select any value of m, and we are still fine. But instead of using male and female, we could choose to use the female number of rabbits, the number of females, and the total population. And now these variables are no longer independent. So if I say that there are 231 female rabbits, then of course there must be at least 231 total rabbits. So this region is excluded. We can't have a total number of rabbits that is less than the number of female. And so these two variables are not independent, and these variables are independent. And you see that if you take any range here and any range here, the total number is going to be the product. So you have the volume is the total. But inside here, instead, if we take a range of female and a range of total rabbits, we don't get the product, we get less. And so these are not independent. The orthogonality is really something that tells us we have all possible configuration and the things are independent. Okay, another type of orthogonality that it's related but different is the one from statistical independence. So in a variable independence, let's say what we had before, the number of configuration on the x does not constrain the number of configuration on the y, therefore the total number of configuration factorizes. The total number of configuration in x and y is the number of configuration of x times the number of configuration of y. Now, in statistical independence, something like that happens when the probability factorizes. So the probability of finding x and y is the probability of x times the probability of y. Now, of course, you can have something that it's not statistically independent in phase space. So the fact that you have independence of variable does not imply that you have statistical independence. But the link is that if you want to allow things to be able to be statistically independent, if you want to allow that there are some probability that factorize, well, these probability are going to be, these are probability densities actually, and they're going to be divided by the number of k's. So if you want this to factorize, well, this needs to be able to factorize too. So the idea that the system is decomposable into independent degrees of freedom is equivalent to say that the system allows statistical independent distribution over each degree of freedom. It doesn't mean that it always has them, but it says I can have them. And if I can have them, then the number of configuration must factorize, and therefore these two conditions are equivalent. Well, another thing that we can say that are equivalent are the link between information independence and statistical independence. And so the idea is that whenever you have statistical independence, you have information independence and vice versa. So how does that work? Well, these are simple proof, and if you want to follow them more closely, you can pause and read them. But the idea is that if we start from here and go here, we can take the Shannon entropy for the joint distribution. And then, since we're assuming statistical independence, we can say that the joint is just the product of the marginal. And we can use the property of log such that the product of the logarithm is the sum, the logarithm of the product is the sum of the logarithm. So we break this expression into two, that inside the logarithm here there is only x and here only y. And then we can separate this integral now because there is the part with x and the part with y. So we take the part with y here, and this is the part with x, and this is the part with x, and this is the part with y. And now the integral of the distribution by itself, that's 1, because probability are normalized. So this integral goes away, and so you just have the integral of rho x log x and rho y log y. But these are the information entropy for each marginal. And so you do have that assuming statistical independence gives you this information independence, the fact that the entropy is the sum. Now you can go the other way. So we assume that we have information independence and we show that we're going to have statistical independence. And how we do it? Well, we start with the sum of the entropy on the two marginals, which is this expanded. And again, now we use the opposite of what we did before. We basically say, okay, this marginal is just the integral of the joint along y, and this marginal is the integral of the joint along x. And now we can factor in these two terms. We are going to have the logarithm, the sum of the logarithm is going to become the logarithm of the product. And then what we do here, we do this trick where we first divide by rho x, y, and then we multiply. But then this multiplication, we again use the property of the logarithm and we take it out in a new term. And now this is the information on the joint. And so if we have that this sum is equal to this must be 0. And if this has to be 0, then the only way that it can do it is that if this logarithm is equal to 0, which means that the argument of the logarithm has to be equal to 1. Therefore, the joint distribution has to be the product of the marginals. Okay, so we have essentially that if the system allows a statistically independent distribution over each degree of freedom, then the system must allow information independent distribution over each degree of freedom and vice versa. So our variable independence now has 3 different characterizations that we can use. And notice that these are sort of similar characterizations that we used in our single degree of freedom, and so that's nice that everything sort of works. And the last one that we have is in terms of uncertainty for peak distribution. And what do I mean by peak distribution? These are going to be distributions that are very, very tight, that they're very, very small. And therefore, it's essentially okay to think these as very small Gaussians, and only the average value and the standard deviation are going to be significant, and we can ignore all the other higher moments. Now, in this case, then the fact that we have statistical independence is the same as saying that the uncertainty factorizes. And again, the uncertainty you can represent with these ellipses, and then what happens is that these are on each degree of freedom, and when you put them together, since they're going to be statistical independent and the uncertainty is going to factorize, you're going to basically have some kind of oval-shaped figure. And how can we show that? Well, again, let's go in this direction first. This is just the expression of the covariance matrix, and the determinant of the covariance matrix really measures the spread of the distribution. And if we have a statistical independence, then the covariance is 0. Therefore, the determinant is the product of the diagonal terms, which are the variances, and therefore the total uncertainty is the product of the variances. Now, if we go in the other direction, the first thing that we note is that the covariance matrix is a symmetric positive semi-definite matrix, which means all the eigenvalues are 0 or greater. In fact, they're going to have to be non-zero if we really have a distribution over phase space and not something on, let's say, on a line. And for these types of matrices, there is something called the Hadamard inequality that tells us that the determinant has to be less or equal to the product of the diagonal terms. And the equality is satisfied only if the matrix is diagonal. So if we're assuming that the uncertainty factorizes, then we're basically saying, okay, this matrix have to diagonalize, and therefore all the covariance terms are 0. And now this, again, only because we are in something that we can approximate to a Gaussian, then the fact that you don't have a covariance means that you have independence. And again, I strongly say that in this specific case, because in general, statistically, the fact that you have a covariance that is 0, that you don't have a linear correlation doesn't mean that you don't have any correlation. But in this case, just because only the second moment is going to be significant, is going to work. Okay, so then we have yet another characterization of this idea of independence of degree of freedom. So the fact that we can separate the system in independent degree of freedom is equivalent to say that we can do it at a statistical level for some distribution, and we can also do it for some peak distribution, so that we can always have things that at least that there exists this distribution that factorize in this way. Okay, so basically what we've seen is that we have the equality of these three conditions: the fact that we have independence at the variable level, the independence that we can have statistical independence, the fact that we can have information independence, the fact that we can have uncertainty factorizing in peak distribution. These conditions are all equivalent, and they're all equivalent to say we have orthogonality between degree of freedom. We can decompose the system into orthogonal degree of freedom. I say, okay, so basically we have two, let's say, constitutive assumptions of Hamiltonian mechanics, two assumptions that Hamiltonian mechanics has to satisfy, the system has to satisfy before we can say that the system is Hamiltonian and it actually works with those equations. The one is of determinism and reversibility, the fact that the system undergoes a deterministic and reversible evolution that specifying the future is equivalent to specifying the past and vice versa, and that the system can be broken down into independent degree of freedom, right? So we have these two things, and the question is whether these two things are enough. Because we saw before, Hamiltonian mechanics conserve the volume, but also conserve the orthogonality, where now we're just basically saying that there is determinism and there is this orthogonality, there are independent degree of freedom. Now, is the fact that when we map, we have a deterministic and reversible map, is this preservation of independence something that is there already in the assumption of determinant reversibility, or it's an extra assumption in the sense that we could have determinants of reversibility without preserving the independence of the degree of freedom? And it turns out that you don't need an extra assumption, and let's look at it in the final case to build some intuition. So suppose you have two integer variables with x and y that can be 1, 2, or 3, right? So we could have 3 possible types of map. So let's say that x are the rows and y are the columns. We could have a map that just maps x to x, so rows to rows, and y to y, column to column. So for example, this column is mapped here and this row is mapped here, right? So now this type of map is going to preserve statistical independence and variable independence as well. Because you can see that we have 3 times 3 cases, we have 3 times 3 cases, so the number of cases is good, we have variable independence, but we are also preserving statistical independence because if we have a distribution over x, that is still mapped to a distribution over x, just with the values switched around, okay? But we could do something a little bit more complicated. We could map elements of xy to elements of xy without preserving x and y. So for example, we are moving this element here and this element here and so on. And you see none of the rows are preserved, none of the columns are preserved. So if you had a distribution that was that was independent of the x and y, that would factorize, once we perform the map, the distribution does not factorize anymore. So we have violated statistical independence of the map. We have scrambled things around. But you see, we're still preserved the variable independence in the sense that we still have 3 case times 3 case. And these are the type of things that our Hamiltonian mechanics are going to allow. You're going to be able to put, during the involution, you're going to be able to create correlations between the degrees of freedom, right? And so you're going to lose the statistical independence, but the variable independence is still there. The product of the areas is still the volume. That you're not going to lose. Now, you could also have a map that merges some case. So for example, this case and this case are mapped to the same case. And of course, if we do that, then not only we're going to violate statistical independence, but we're also going to violate variable independence, because now we do not have the product anymore. We're losing states. And now see that if we were to make a map like this, then of course we are losing reversibility. And so if the map is deterministic and reversible, the number of states here have to be the same number going back. And so if we have a deterministic and reversible map, what happens is that when we have independent variable, this product of the case is maximal, and so we're going to a case where we have the maximum number of possible joint states. When we're mapping it, we are also always going to map it to this maximal case as well. So we cannot map things that are that have this variable independence to think that they're not variable independence, deterministic and reversible. So there is really no extra assumption that is needed. These two are enough. So once we say that we have the independence of the degree of freedom, then we have the ability to count configuration for each independent degree of freedom. And this is what omega allows us to keep track. It allows us to keep track of the configuration on each independent degree of freedom. Those areas are the count of configuration, and whether these are independent or how much independent they are. And this orthogonality is that the omega is going to keep track, is really keeping track of in the independence of the degree of freedom. And then when we do our add the assumption of deterministic and reversibility, then we are going to conserve a number of states, and the count of state is maximal for independent degree of freedom. And so once we are preserving both the areas and the product, what's going to happen is we're going to preserve both the volume and orthogonality, and therefore we are going to preserve the whole omega, and therefore we are going to be able to recover a Hamiltonian. So that's basically it. That's all there is in Hamiltonian mechanics. There is the assumption of independence of degree of freedom and the assumption of determinate reversibility, and you can understand all the geometry of classical mechanics based on these two terms. So I hope you enjoyed this video, and again, this is the outcome of our research on assumptions of physics, and if you want to see more detail, there is going to be a link below for the book where you can actually see all these things in a lot more detail, and you can also look at our website for all our activity, and we also have a separate channel in which we're actually trying to do research, so if you're really interested in how the project is developing, you can also go and see things there. So thank you for your attention, and see you next time.